Hello. My project is entitled PiezNo, Harvesting Kinetic Energy Through an Application of the Maxwell-Faraday Equation via Electromagnetic Induction. So currently in the status quo, the main way to harvest kinetic energy is through piezoelectricity. But this method is extremely expensive, delicate, and therefore ineffective. For example, when I dropped piezoelectric crystals from a height of 10 centimeters, they shattered almost instantly. Which is my project aims to create a better alternative to piezoelectricity, specifically using three main design criteria. First, it should have a higher energy output than piezoelectricity. Second, it should be more cost effective. And finally, it should be relatively compact and therefore easy to use, as well as less delicate, in order to be used practically. In order to achieve this, I used the Maxwell-Faraday equation to create electromagnets that would harness energy through vibrations and kinetic energy. Now, the Maxwell-Faraday equation relates electromagnetic induction to magnetic flux, and the generalized form can be simplified to a simple equation that says induction is equal to the number of turns times the magnetic flux over time, which means that if you move a magnet through a metal coil and divide it by the number of seconds, you'll be able to create an electric output. And so I hypothesized from that the medium-sized small sphere would be the most cost-effective, or more cost-effective. This was because I thought that these cylinders would not be as cost-effective because of the reduced range of motion, similar to the one shown here. And as a result, these spheres would be much more cost-effective because they would have a greater degree of motion. And the medium sphere would be located in the Goldilocks zone of generation cost efficiency. In order to create my mechanisms, I used CAD drawings on Fusion 360 software. And after printing them out on a 3D printer, I coiled them 300 times with copper wire and put a small niobium alloy magnet inside, similar to the one here, and it depended on each size of the mechanism. I tested these 8 mechanisms in 4 main procedural phases. The first phase was the natural vibration and practicality phase, or the NVPP. In this phase, I hooked the ends of the wires of the mechanisms onto an oscilloscope and put the mechanism inside my pocket. I then used a metronome to monitor my walking rate, and I would walk 20 seconds with that mechanism inside my pocket. After that, I was able to collect the data in voltage. But I want to also show electric potential, not only show electric potential in volts, but also electric generation in watts, which is why I underwent phase 2, or the wattage calculation phase. In the wattage calculation phase, or the WCP, I attached a 100 ohm resistor to the ends of the mechanism, and tested the phase 1 experimentation once again. Because of this, and I used Ohm's law, I was able to gather the amps, and as a result, the watts by multiplying volts times amps. I combined the data into 2 main graphs of voltage generation and wattage cost efficiency. Now, from these 2 graphs, we see that the main trend is that the large sphere, or the black lines, are not only the most generative, but also the most cost-effective. And as a result, this was the greatest mechanism in this phase. We also see that the medium small and the medium large spheres lagged in second and third place respectively, and the cylinders were in fact actually extremely far behind, probably because of the lack of degrees of motion that I mentioned in the hypothesis. Then I used a trapezoidal Riemann sum to obtain a watt-hour value for not only the generation and the cost and watt generation, but also the cost efficiency. And the tabular analysis was done to show that the large sphere was in fact much more generative than piezoelectricity, and was also much more cost effective. But in addition to just finding wattage, I wanted to see what the true potential of this project was if we change another variable, or in this case coils, rather than magnet size and coil size. And so I changed the number of coils in the large sphere. I was able to use 2,500 coils to create a mechanism, the large sphere, with 2,500 coils instead of the standard 300. This is notably much larger, but it was able to generate a lot more electricity as well. After undergoing the phase 1 and phase 2 testing for multiple coils, I was able to use regression technology to map these data. I used a logistic function to map not only the short-term data, but also the long-term data as well, and to match the both flow of the short-term and long-term trends. And this can be seen not only the generation, but also the regression. And then so I was able to map 2 functions to these graphs, and using the second derivative test was able to find the point of inflection, or the point of the highest slope for both of these graphs. On the generation side, it was actually 3,473 raps, and on the cost efficiency side, it was 2,489 raps, or very close to the 2,500 coils that I already did. The final phase of testing was phase 4, or the circuitry application phase, or the CAP. In this one, I used several circuitry elements to create a breadboard circuit that would not only transform the AC voltage into DC, but also flatline the large tumultuous vibrations into a plateau-like data. So first, I used 4 germanium diodes that have a relatively low drop voltage to convert the data coming in from the AC into DC. Then I put the data through a capacitor, a 1 farad capacitor, to act as sort of a water tank to fill up the charge. Then the charge was released based on an FET or MOSFET, which is actually software controlled using a TI Innovator hub connected to the breadboard and connected to its calculator. I was able to write a program on TI Basic and to execute it to monitor the amount of charge and release it to the LED controlled by the resistor if it reaches a certain threshold. And so if we run the program and we shake this as similar to human motion, we see that it's currently generating about 0.5 volts consistently through the entire circuit in DC and plateaued. So that shows a much wider scope of the application for the project. And so after gathering all this data, underwent a statistical analysis to ensure the accuracy of the data. And on the statistical analysis, I used a t-test and a Mann-Whitney rank sum to not show the data was in fact together, but also actually extremely variant, because I tested it between the new large sphere and the piezoelectricity. This can be shown in the median analysis, because the data for the new large sphere was very different from the piezoelectricity data, because the median was at almost 3 milliwatts, whereas piezoelectricity was at 0.006, and many data points were at 0, as can be seen by those two analyses. And from this we gathered our conclusion, that while the hypothesis was proven incorrect, because the large sphere was a more cost-effective one compared to the medium small sphere, all three of the design criteria were met by 4 of the mechanisms. The medium large sphere, medium small sphere, medium large sphere, and the new large sphere in the third phase as well. And the new large sphere was actually 34 times greater output than piezoelectricity and 11 times more cost-effective, therefore showing that a mechanism that is better than piezoelectricity and passed all the design criteria with flying colors could be created. Now this has many applications, most notably within human motion, as can be seen in phase 1, 2, and 3. Now in phase 1, 2, and 3 we saw civilian use of human motion, but it also exists in the military field. Currently the military often use unsustainable energy sources because they're constantly shifting their location, and as a result don't have time to set up solar or wind farms. But by putting these mechanisms on the body of these soldiers themselves, they will be able to generate electricity through human motion, rather than being obstructed by it. The second main area of application is the transportation field. And currently in the transportation field, regenerative braking is being implemented, as in using piezoelectric film to convert mechanical energy into electrical energy, instead of it being lost by heat from acceleration and deceleration. However, these mechanisms are implemented using inertial properties. The magnet will be able to spin around the mechanism as inertia works, and thus will be able to be more cost effective in the transportation field, making it cheaper and therefore more effective to the consumer. Finally, the main area of application is the industrial field, because currently large industrial machinery not only take in a lot of carbon and release carbon dioxide, but also produce a large vibrations. By placing these mechanisms on the side of these machinery, we will be able to harvest the energy coming off of these industrial machinery, as a result making it self-sufficient, making it a net zero energy building, or NZEB, which are on the rise in American society, and actually can increase exponentially through the application of these mechanisms. In the future, I hope to add more variables, as I did with Phase 3, and not only adding more points in Phase 3, but also experimenting with various distance between magnet and coils, and also adding more shapes and sizes to further the bell curve that would be formed by this experiment. I also want to add more circuitry such as supercapacitors to see what the true potential of this project could actually be, and finally create an actual application for the experiment by placing it in such as a phone charger rather than just lighting up an LED. Although, just like any science fair project, there were a few errors involved. Two main systematic errors were the overlapping and uneven wrapping methods of this mechanism, as you can see here, and can be prevented in the future by changing the procedure to have a robotic mechanism coiling mechanism. And the second main error is that the attraction between the magnet and the clips was too great, as can be seen here. The strength of the niobium mallet is very strong, and as a result actually caused small chips in the magnet that are no more than 2 millimeters big, therefore throwing off the data perhaps a little. This was prevented by using plastic alligator clips, but still may have thrown off the data very slightly because of the 2 millimeter chips. There are also two main random errors. First of all, the very thin 32 gauge magnet wire has a very high tendency to get tangled up, and similar to the one here, may have altered the magnetic length and restricted the flow of electricity through the wire. Secondly, the oscilloscope wires may have restricted the motion of the mechanism. As it was placed in the magnet and clipped at its two ends, it may have restricted its motion instead of being a 360 degrees of motion. However, all in all, these errors did not affect the project as much and was reduced by having over 300 total trials. And as a result, the main gist of this project was I was able to create a more cost-effective alternative to piezoelectricity by not only creating more generation but more cost efficiency that can be used in the future to be more cost effective than piezoelectricity and in the status quo.